Welcome everyone to Zahid's data mining channel once again. My name is Zahid Islam and today I will be talking about a missing value imputation technique called FIMUS. We published this paper in 2014 in knowledge-based systems and the paper is available online. So this is the URL. You can actually go and download the paper from their website. So missing value imputation. What is missing value imputation? That's the first question, right? So if we collect a data set, say for example, this is an example of a toy data set where you can see we have 15 records and 3 attributes: education, salary, and position. So often for various reasons data sets are collected and that is analyzed for various data mining purposes, knowledge discovery, knowledge extraction, future prediction, etc. But when you collect a data set, generally there will be some missing values, some values that are missing, right? And that can happen for various reasons. It can happen because the survey questions were not answered. It can happen because the sensors did not work properly, battery went flat, and so on. So when you have missing values, then if you can actually understand or study the data set very well, carefully, then you can guess, you can make an educated guess to estimate the values of the missing data. Say for example here, for record 1, salary was missing, but then by understanding the data set, by reading the data set, understanding the data set, analyzing the data set, a system can predict the value. Say for example, in this case, this system is predicting 85.2, whereas the original value, if we look at, is 85. So here in this case we have the original value. We are then randomly creating some missing values and then applying our technique to see whether our technique can impute it properly, and that's why we have a ground truth original value, so we can then evaluate the effectiveness or accuracy of the imputation. But then in real life you will not have the ground truth, so you then have to rely on this imputed values. Imputation can be very useful in many ways. It can increase data analysis accuracy or quality. For example, classification accuracy can be improved by imputing. So here we made a early experimentation where we showed that if you impute a data set and then build a classifier, generally that classifier is more accurate than the classifier that you build from a data set with missing values. So if a data set has various missing values and then you build a classifier, the accuracy may not be as good as if you do it after imputing the values and then building classifiers. So now let us explain the basic concepts of our proposed technique, FIMUS. So what we do, we first study a data set and we build we actually analyze in couple of different ways. Say for example, first thing is coappearance matrix. So we can actually build a coappearance matrix for every pair of attributes, where in this case, in this example, is showing education and position, so these two attributes, and we are calculating what is the coappearance between MS and L. L possibly means lecturer, P possibly means professor, so whatever it is. So MS and L, what is the coappearance value for that? So in these records, there are 15 records. This is a toy example only. In real life, your data set will be very big. Your number of attributes will be big. But in this example, there are 6 records where the education is MS and position is L. And there are 9 records where education is PhD, position is P, professor. So similarly, we can build a coappearance matrix for all attribute pair. So if the attribute pair is a categorical, the both attributes in the pair are categorical attributes, then you can directly build this coappearance matrix. But if one of the attribute is numerical, then you have to discretize the numerical values into different bins or categories, and then you can do the coappearance analysis. Similarly, the next thing we do is the correlation matrix, and the correlation matrix is the correlation between two attributes, as we know, statistical correlation. So if two attributes are numerical, the correlation can be calculated easily, but if there is a categorical attribute also, then there are ways we can calculate correlation analysis. Please feel free to read the paper, download the paper and read the paper. The details are in the paper. Similarly, the third thing that we do is the similarity metric. Similarity metric is for every attribute individually. So after we categorize, or all the values are categorical, we can then calculate similarity between two different values. For example, MS and PhD. What is the similarity between MS and PhD? The values of one attribute, the domain values for one attribute. We can have a matrix for their similarity. One categorical attribute can have domain values PhD, MS, bachelor's, professional doctorate, and so on. Then which one is similar to which one? So that similarity, there are existing techniques and we use one of them. Feel free to read in the details in our paper, and we can then calculate similarity between these two values. Now this is the basic concept. After we understand the basic concepts, this is the mechanism of our proposed technique, how it works. Let me explain this figure a little bit more clearly. So Rij it means that it is the ith record. R is the record, I is the ith record, and J is the jth attribute. So it is the jth attribute of the ith record. So, and we can see that, for example, this record has a missing value. Okay, so we don't know the value of the jth attribute for the ith record, and we want to impute it, right? But we know that the possible values are x, y, and z, because we know the domain values of an attribute. So we know that possible values are x, y, and z. Now we have to impute it by one of them. So now this approach is basically kind of a voting approach. So we will calculate vote for x, vote for y, and vote for z. Whoever gets the maximum vote, that will be the imputed value. How do we do that? So we consider then another attribute, and another attribute of the dataset, say for example P. So Pth attribute, so this is the ith records Pth attribute, and then say for example in the Pth attribute, the value that is appearing in the Pth attribute is L. So then we can calculate, or we can then have a look at the coappearance value of X and L. From our previous thing, this coappearance metric, you can see that if this value is missing, this value is missing, we can find out the coappearance of P and PhD, right? So that coappearance is 9, something like that. So we know that CXL, that's the coappearance. And then we also know the frequency or number of occurrence of L in that attribute. So we divide that CXL by FL, and that's the voting for X based on L. Okay, so we call it Vx. So that's the primary voting, N, so for X. Now we also take another thing into consideration, that okay, in this particular record L appeared, but other possible values for this attribute P were M and N. So what is the coappearance matrix for coappearance value for M and X? We also know that CXM from the coappearance matrix, we know that. And then what we do is we calculate the vote for X based on M and N as well, and that is done using this equation, where we consider the coappearance matrix of M and X divided by the frequency or number of occurrence of M, and we multiply it by the similarity of L and M. So how similar L and M are? So if they are very similar, then the vote for X due to M will have better weight. If M is not so similar to L, then it will not have as much weight. And this is how this equation will help us to get the secondary vote for X, that due to the values that did not appear, but those are quite similar to the values that appeared in the Pth attribute. So then these two different votes are then combined together with a lambda. So lambda tells us that how much weight we will give on the secondary values, the values that did not appear but if they would appear, the influence of them. So if you consider lambda equals 1, that means the influence of these secondary values will be 0. 1 minus 1 is 0, so that would cross out. So the only we would impute based on L, the value that is appearing. But if we consider lambda equals 0.7, that means 70% weight to the value that is appearing and only 30% weight on the other possible values, something like that. So in we did some experiment, and it looks like generally a 70-30 ratio gives us the best result. So but this technique gives us that option that you could also consider other values that could appear, although did not appear, but could appear in this record, and then what would be the imputation. So once we get this imputation voting for L and M and N, if we consider them, then the next thing we do is we multiply that with RJP. RJP is the correlation between jth attribute and the pth attribute. So what it says is that if pth attribute is heavily correlated with the jth attribute, then RJP value will be high, and these vote will be multiplied heavily, because the voting for X is not just done based on the pth attribute, but you have to understand that there are similar attributes, which are similar to the pth attribute, like kth attribute, lth attribute, and other attributes are there. So all attributes will actually be used to calculate the vote for X one by one. So when we are calculating the vote for X based on the pth attribute, we also consider the relationship or correlation between jth and pth. If pth attribute is not correlated at all, then this will be 0 and the vote will be all 0. So there will be no influence of this pth attribute in calculating the voting of the jth attributes values. So once we get this RJP, we get the final vote for X based on pth attribute. Similarly, we will repeat the process for the final vote for Y and final vote for Z based on the pth attribute. So now we have vote for X, vote for Y, and vote for Z based on the pth attribute. Then we will go to the next attribute, maybe Lth attribute, Mth attribute, Kth attribute one by one, and then we will again calculate the vote for X, Y, and Z one by one, and we will add them up. So finally at the end we have vote for X, Y, and Z based on all other attributes of the dataset, and then we will calculate, or we will see whichever value has got the highest vote will be the imputed value for this. So this is our FIMUS tech approach. Now we applied this on a dataset called adult dataset and also many other datasets, but in this example we are showing the results on adult dataset, and we actually made the missing values using total 32 different combinations. So 1% missing value, 3%, 5%, and 10%. This is the missing rate. That means 1% of the values are totally missed, are totally lost, or made missing. And then in this model 3% missing values. But then when we made 1%, then we could use two different missing model, overall or uniformly distributed. Overall means overall 1% values are missing, whereas uniformly distributed means 1% from, but each of the attributes has exactly same number of missing. So that is that. And then there are three different missing models, simple, medium, complex, and blended. Simple means in a simple model, so if we are making 1% value missing, then each record can have at most one value missing. In a medium approach, each record may have up to 50% of the attributes value missing, and in the complex up to 50 to 80% attributes value missing for every record, and blended is a mixture of all of them. So there are 32 different combinations because we wanted to see that in all possible scenario our technique performs well, and we can see that in all possible scenario of the adult dataset, 32 possible combinations, FIMUS gets the best result in terms of RMSE. This is a metric to estimate the accuracy or effectiveness of an imputation, and in terms of D2 as well. So it achieves very good result. Here we used many other datasets, and we can see that in terms of RMSE, our technique achieves 288 cases. Out of 288 cases in 9 data sets, our technique achieves 275 cases, the best result, and so on. So nice, 95.49% good result. So it's a very good technique. Feel free to download the paper and read it.